according to the standard model that scientists have constructed through decades of rigorous investigation. At the very instant of the universe's great explosion, an immense quantity of energy commenced its transformation into the initial fundamental particles, such as electrons, protons, and neutrons. Envision that extraordinary scene, though we can only conjure it through mathematical frameworks and experimental simulations, a nascent cosmos, searing with heat, where energy surged like an infinite ocean of flame, abruptly condensing into those minuscule particles that form the bedrock of everything we recognize today. Simultaneously, antiparticles, the counterparts with opposite charges to these particles, emerged in pairs, akin to opposing twins, perpetually poised to collide and annihilate one another. Upon encountering each other, a particle and its antiparticle would instantaneously obliterate themselves, vanishing in a brilliant burst of energy, all converting into liberated energy, much like a silent detonation echoing through the vast expanse, leaving naught but emptiness in its wake. If this theory held without deviation, nothing in our universe ought to exist, for the perfect equilibrium between matter and antimatter would result in their complete mutual destruction, yielding a barren, frigid cosmos devoid of stars, planets, and certainly devoid of us contemplating such matters here and now. Yet, we do exist, drawing breath, perceiving the world around us with its twinkling stars adorning the night sky, its surging oceans, and its bustling cities, all testifying that at the universe's birth, the initial balance experienced a subtle deviation, precipitating a symmetry breaking in the cosmos. This was a diminutive yet fateful aberration, comparable to a single grain of sand altering the course of an entire river, permitting matter to persist in slightly greater abundance than antimatter, sufficient to construct the entirety of the universe we inhabit. So, what accounts for this deviation? It remains one of the profoundest enigmas in contemporary physics, a query that keeps scientists across the globe awake through the night, laboring in subterranean laboratories, attuned to the hum of colossal machinery, and eagerly anticipating clues flickering across computer screens. The scientific community terms it the baryon asymmetry problem of the universe, where baryon denotes particles like protons and neutrons, the fundamental building blocks of atoms. To elucidate this phenomenon, some have proposed a bold hypothesis known as supersymmetry theory. In this framework, each known fundamental particle possesses a heavier partner, namely a supersymmetric particle, much like each of us having a twin sibling who is stronger, more massive, and capable of reshaping the rules of engagement. It is these particles that purportedly induced the asymmetry in the universe's early phase, engendering that slight deviation, akin to a gentle nudge sufficient for matter to prevail in the existential struggle against antimatter. Supersymmetry theory transcends mere abstraction. It has been extensively debated at international gatherings, such as the SUSY 2025 conference held at the University of California, Santa Cruz in August of this year, where hundreds of physicists from around the world convened, exchanging ideas in spacious lecture halls, with applause resounding when someone unveiled a novel model, and tense silences prevailing during debates over evidence. Recent updates from the Large Hadron Collider, as reported in analyses by the Atlas and CMS collaborations in 2025, continue to probe for supersymmetric signatures across diverse final states, including boosted particles and extended datasets. Yet direct evidence remains elusive, prompting some scientists to feel disheartened while spurring others to delve deeper. For as one physicist has remarked, the absence of evidence is not evidence of absence. Moreover, emerging theories in 2025, such as those exploring hypercharge breaking scenarios, suggest that spontaneous symmetry violations in the early universe could further explain this baryon excess, potentially integrating with supersymmetry to provide a more comprehensive picture, to uncover traces of these supersymmetric particles. Scientists at the world's premier particle physics laboratory, namely the European Organization for Nuclear Research, have initiated a program entitled the Baryon Antibaryon Symmetry Experiment, abbreviated as BASE, with the objective of comparing the fundamental properties of protons and antiprotons. They operate in lengthy, dimly lit corridors beneath the landscapes of Switzerland and France, where the air is chill, the machinery drones like the heartbeat of the Earth, and anticipation permeates each new trial. This experiment seeks to identify minute differences that might violate CPT symmetry, a amalgamation of charge, C, parity, P, and time, T, thereby offering insights into the asymmetry between matter and antimatter in the universe. In 2025, physicists employed exquisitely precise magnetic pulses to transition an antiproton from one spin state to another, akin to manipulating a diminutive magnet at the quantum level. This marked the first instance in human history where antimatter responded to controlled quantum manipulation successfully, a moment that elicited cheers in the control room, with beaming smiles and proud shoulder pats, as they breached a new frontier of science. Specifically, in July 2025, the base team at the European Organization for Nuclear Research published findings in the journal Nature, demonstrating coherent quantum spectroscopy of a single nuclear spin, a trapped antiproton, unlocking avenues for more precise measurements of antimatter's magnetic properties. Prior experiments could only compare static attributes such as mass, charge, and magnetic moment, much like viewing a static painting without observing motion. Thus far, even within margins of error as fine as 1 part in a billion, no discrepancies have been detected, occasionally leading scientists to moments of discouragement yet steadfast perseverance, knowing truth often lurks in the minutest details. But now, we have progressed beyond mere measurement into a novel era of dynamic control, also paving the way for experiments of unprecedented precision, such as guiding a tiny particle's whirl in a magnetic field, heeding its whispers through data streams. If, during such quantum transitions, the antiproton exhibits even a slight behavioral divergence from the proton, it would constitute direct evidence of a flaw in the universe's symmetry, a revelation capable of sending shockwaves through the scientific world. With headlines proliferating across media and fervent discussions erupting on social platforms, it is these subtle flaws that have enabled matter's endurance, fostering our existence today, from distant stars to blossoms unfurling in your garden. Thus, why did matter triumph over antimatter? The answer resides in the conduct of those fundamental particles composing our world, particles invisible to the naked eye yet influencing all surroundings. Scientists endeavor to discern how nature's foundational symmetries fracture by observing the decays of heavy particles generated in colliders, where particles clash at velocities nearing that of light, recreating miniature Big Bangs, with resounding clamor and data cascading like a river of knowledge. Indeed, as early as 2017, researchers first detected decay in baryon B, uncovering indications of CP symmetry breaking, a historic juncture that saw physicists embracing in jubilation, for it was the inaugural observation of this phenomenon in baryons comprising matter. By 2021, scientists observed analogous symmetry breaking in another baryon type, bolstering confidence in an underlying cosmic trend, akin to a subterranean current gradually surfacing. And 2025 has heralded even greater strides. In March, the LHCb team at the European Organization for Nuclear Research announced the observation of CP breaking in the Lambda Beauty baryon, Lambda B, a heavier relative of protons and neutrons, drawing from over 80.000 decay instances, demanding utmost patience and precision. Subsequently, in July, they corroborated charge parity symmetry breaking in additional baryon decays, published in Nature, furnishing compelling evidence that this asymmetry persists at the baryon level, particles constituting most familiar matter. This is profoundly persuasive proof, invigorating the scientific community, as it draws us nearer to comprehending why the universe brims with matter rather than antimatter. Further bolstering this, 2025 theories like Haxaverse baryogenesis propose that quantum chromodynamics axions could unify explanations for both baryon asymmetry and dark matter, while our investigations into generalized coupling gravity explore gravitational contributions to this imbalance. So, what precisely is CP symmetry? It constitutes one of the elemental principles shaping the universe, a tenet that nature appears to adhere to, albeit imperfectly. Per this rule, any physical process, if inverted from left to right, termed P, or parity symmetry, should unfold normally, as if gazing into a mirror where events proceed unaltered. Then, if you reverse the charges of all particles, namely C, or charge conjugation, matter and antimatter ought to exhibit identical behaviors, like two sides of a coin. Yet, in reality, nature deviates subtly from this precept, rendering the universe more intriguing. In experiments, when particles and antiparticles decay, the probabilities of certain outcomes display minor variances, akin to a game of chance where one side holds a faint advantage. For instance, the likelihood of a baryon decaying into a combination including a proton might exceed that of its antibaryon counterpart by a few parts per thousand, a disparity so minute that supercomputers are requisite for detection, yet ample to forge monumental differences in cosmic history. This infinitesimal deviation is CP symmetry breaking, and the 2025 discoveries from LHCb, such as observing CP breaking in baryons containing beauty quarks, have inaugurated fresh research avenues, intimating potential new forces or undiscovered particles beyond the standard model, like missing puzzle pieces in the cosmic tableau. Nevertheless, scientists acknowledge that the observed differences thus far are too feeble to account for the universe's entirety today, comparable to a modest flame insufficient to warm an entire chamber. There may yet exist other particles or mechanisms undetected, concealed within the vast data troves from the European Organization for Nuclear Research. Consequently, in 2025, the European Organization for Nuclear Research has inaugurated an entirely novel apparatus, dubbed TELMAX, a new experimental beamline for antiprotons, capable of decelerating antiprotons produced in the collider to near stasis, akin to taming a tempest to scrutinize each raindrop. This device, synergized with enhancements in base such as rapid cooling systems and cryogenic penning traps, facilitates unprecedented control over antimatter, with heightened accuracy, unlocking prospects for transporting antimatter to distant laboratories, as demonstrated in the BASE STEP project spanning late 2024 and early 2025, where protons, proxies for antiprotons, were successfully conveyed across the site in a transportable trap. It is hoped that through forthcoming experiments, we might glimpse the universe's inception and unravel the ultimate secret of all existence, an inspiring odyssey where each modest discovery bestows joy and hope upon humanity, reminding us that the cosmos harbors myriad mysteries awaiting revelation, and we, mere mortals, are steadily lifting that veil.